Good day everyone. For today, we will talk about Solar Smart, designing a solar energy generator for homes using Mathlab and Simulink. First, let me introduce to you with my groupmates. I am with Jean Ann Forcadella, Eileen Madamba, Shaira Joy Reyes, Arabella Valle, and I am Luis Alrain R. Olivar. Homes are designed to operate on a stable 240 volts of alternating current. This steady AC supply is what needed for our appliances like refrigerators, air conditioners, and washing machines. Thus, without the stable AC, appliances may malfunction or fail to operate. Thus, we are needed to provide a properly and regulated supply, which can be solved with the solar photovoltaic panels. It generates direct current, but with the help of a conversion, we can use it as an alternating current. Their output is highly dependent on environmental conditions such as solar irradiations and ambient temperature. At the midday, under strong sunlight, for example, 1,500 watts per square meters at 25 degrees Celsius panel, it can be reached maximum power output. However, in mornings, evenings, or during cloudy and rainy weather, the voltage drops significantly. In simulation in our Simulink, the PV array produces about 120 volts DC, which isn't enough for direct home use or grid connections. This variability means that the raw PV output must be converted to stabilize before it can be served to household demands. Thus, we need to have this DC to DC conversion to step up our voltage, DC to AC for inversion converts to AC, filtering to purify the waveform, and ripple reduction to stabilize variable PV input. Now let's go to our Simulink to see our simulation. So now, as you can see in this circuit, it is the circuit design elements. So it includes the solar power generations with integrating elements such as the PWM generators, diodes, IGBTs, capacitors, and a graphical user interface to control the inverter and boost converters, temperatures, and irradiation constants. They are set for 505 for this trial, which are connected to capacitor to reduce ripple function. And to complete this setup, we also include scopes in order for us to see the results. As you will notice, there are 3 scopes in this diagram. The first scope is the measurement of the voltage from the PV array, and then the second one is after the boost off, after the IGBT diode or the RLC. Then the third one is after the conversion from DC to AC. Okay, now let's see the simulation results from our Mathlab Simulink. So, as you can see, we set up the PV array with parallel string of 20 and series connected modules per string as 5. Now let's see the output of the PV array only with this figure. So as you can see with this first figure, we are only able to see the voltage going up past 150 volts, but wasn't able to reach our needed, which is the 250 volts. So for the figure 2, this is after the boost up that we did. So as you can see, it reaches 250 DC volt supplies, which is the needed for our appliances to work. So from 110 to 120 volts, we are able to get an output of our panel with the boost up. We we are able to reach and move up the voltage up to the needed voltage. Then for our third figure, this is after the conversion from DC to AC. We are able to get an alternating current result of around 250 volts alternating current, which is the needed voltage for our home.